introduction. Peter is one of my colleagues in civil environmental engineering and also in applied mathematics. He's director of the minor field in computational science and engineering. This is a unique talk, so I don't know how much to introduce about Peter, but he's a professor, as I said, in civil environmental engineering. He did his undergraduate degrees in mechanical and aerospace engineering, Ph.D. at UC San Diego, and aerospace engineering as well, mechanical and aerospace. He works in stratified flows and stratified turbulence modeling. He uses higher order methods for modeling internal and wave fields and internal gravity waves and environmental flows of all sorts. And so I think in the spirit of that, we're going to be have a topic that supports that particular theme. And
yeah.
So I'll turn it to Peter.
All right, so thanks, Chris. And I've got a big page of acknowledgments that I'm going to show in the end. I'd like to thank Alex because he recommended to give this talk. And I'd like to thank him because on multiple levels we've had communications going back from the fall, and I really appreciate his humanity and his candidness on that front. So thanks for having me here. This is an unusual talk. It is in memory of Sumedh, and I was his advisor. Became very close friends. So where I'm challenged is number one, that you want to give a talk in someone's memory, and you often go to conferences where people will just quote all the work someone did, all the publications, all the honors, but they won't reference him as a human being, or her, if this person is passed. And we had a chat with Alex, and I will focus on the technical part, but I'd like to give about 10% snippets of who this guy was, because he was really unique as a human being. On a second level, he did a lot of work, so I'm trying to filter down the essentials, but at some points I might just skip. So feel free to ask me questions. The third and most important one, they always say that the student should sort of surpass the mentor, if I'm allowed to be called a mentor. And Sumedh really did that. I learned tons from him. It was an awesome experience to work with him. So the downside of that is there's some of the things that he's done that I even do not know how to verbalize and explain to others yet. I'm still learning in that regard. So again, ask questions if I block. So I've picked 2 topics from his thesis, 2 core topics that all kind of formed into this flow solver. And it'll be 90% technical. As I said, about 3 slides where I'm going to do some personal snippets. And that's about it. All right, and you're seeing a basketball hoop, an artistic type, and some of you might know what this is. We connected a lot of hip hop and music as well. It was a real connection. So, and I don't think the point is, we want to celebrate his work and him as a human being here. So I have my Greek standard emotional radiation that I do, but I don't want to make this too emotional. It's really to celebrate this guy and his work. Okay, so I got an email in about October 2010 from this kid down in Houston, Texas, who told me, I'm working on ocean acoustics, I want to get deeper into ocean physics, and I really want to attack things from a really advanced computational math standpoint and get really involved in high performance computing. And I said, what God sent me? It's like, who sent this guy to me, right? And we started exchanging emails, and the first thing I told him is that I have grown up in Greece, and this accent comes from an American mother, and do you know Vasilis Spanoulis, who's one of the top stars in Europe now, who spent a totally ineffective year in Houston, nevertheless? They said, of course I know him, right? And then I said, I played basketball for 11 years, and Hakeem Olajuwon is one of my greatest heroes ever. And he was the poet in the paint, and he is fluid mechanics to me. So the point that I'm trying to make is that we communicated on multiple levels. It was the science, but over the course of the years, we talked about, applied math, ocean physics, high performance computing, basketball, politics, all kinds of music, cinema, literature, and just the human condition. He was one of the most thoughtful human beings I knew. And our latest point of obsession was this guy known as the Greek freak, Yannis Antetokounmpo. So Sumedh was a real Renaissance man, and it was a real pleasure to work with him. So he told me, I want to study internal waves in nature, in the ocean, and I want to model acoustic propagation through them. And he showed up. I was in admissions committee that year. I think Steve Strogetz was on it. David, who just walked in, was on it, and a couple other people. He didn't have the best grades, but there was this weird little spark about this guy, and his reference letters showed something very special. And he came here for a visit. He was really nervous, as far as I remember. I'm like, this kid is weird. That was my first reaction. And he turned out to be the nicest human being ever. And we sat down, and he laid out this really ambitious plan. He said, I'm going to get my own fellowship, and I'm going to do this by myself. I'm like, okay, hold your horses. This is not going to be easy, all right? But I think we got something really cool going on. So we never got to acoustic waves going through internal waves, but we got to a bunch of other stuff, and I want to talk to you about that. But I want to give you enough context, all right? This is just a little cartoon. of people sitting on a boat in a fjord. The water is stratified. You may have heard of dead water. And they're measuring some very particular waves by dropping a certain device, which also might be acoustically motivated. So I'm going to show a lot of equations, and I'm going to focus, hopefully, towards the interest of your audience without really overwhelming you. I will iterate that I am not an applied mathematician, but I don't even know if I'm an engineer. I don't believe in labels. I guess what I do is engineering physics. Okay, so some of these things you folks might have a lot deeper insight than I do. All right, so this is a little cartoon. This is a schematic of a transit in the ocean, which could be about 50 kilometers long. It's not drawn to perfect aspect ratio or scale. And the water is well mixed at the top. This is showing a density profile. There's a sharper density transition here known as the pycnocline or thermocline. And it's a weaker density gradient going all the way to the bottom. And you can actually observe these internal type of tsunami waves that are called internal solitary waves. And these consist of often in a deeper water depressions of this thermocline layer that I will call, they're often known as internal solitary waves of depression. So someone told me this could be something created by Edgar Allan Poe. That was Sumedh's suggestion. And they go from deep water into the shallower water. And often in some cases when the thermocline is below the middle of the water column, you get an actual elevation. They have a lot of features similar to surface waves. They're of interest for multiple levels because they drive the energetics of what's called the continental shelf region. So the part of the ocean extending from the shore roughly about 40 kilometers offshore to about 100 meters deep water. They drive biology because they mix the water column and they transport biota or nutrients for various organisms. They control the temperature structure of the ocean. And in many ways, they're responsible for gradients, for temperature differences that are 3 degrees higher, in some cases lower than they would not be if the waves were not there. And effectively, if it weren't for these internal solitary waves, the ecosystem would be totally thrown off. Right? And if you study ocean acoustics or optics, there's a lot of applications here as well. And these same beasts occur in lakes as well. And our lake is a natural laboratory for them. And they play a big role also in controlling water quality because they suspend stuff off the bottom and they mix them around, all sorts of things happen. So you've got these waves. In this context, I'm looking at a slice, I'm just thinking of being two-dimensional, right? So my wave is going in a direction normal to what are called the isobath line or the isotopography lines, right? It could be going obliquely. I'm not going to worry about that for the point of this discussion. And the waves are these two-dimensional patterns of disturbances in the velocity field and a background density field, to the background density field, and just moving from deep water into shallow. And in some cases, we'll get smaller scale patterns internally that are linked to what's called the fluid instability or turbulence. And we'll also drive stuff at the bottom, right? So we really want to model these, and they're a real challenge to model for a variety of reasons, right? The waves themselves, especially in deeper water, do not dissipate a lot of energy, all right? And they do not disperse. So these waveforms pretty much are very steep, all right? So they're very nonlinear, and at the same time they're very dispersive, but the two balance out each other, so you get a wave that's very, very nonlinear and very steep that just shoots across horizontally through the water, from deep water into shallow, all right? And they also will operate through variable bathymetry, all right? So you need to have some kind of complex boundary to your problem, okay? So at the same time, they're nonlinear, all right? So nonlinearity poses a lot of challenges to the numerical simulation of your actual PDs that I'll show in a second. And they're non-hydrostatic, right? What does that mean? That there's very strong vertical velocities associated with these waves themselves, but furthermore with the turbulence that they generate internally. This creates a very, very, very big challenge in terms of the equations that you actually have to solve, which I will show. Okay? As I said, at the same time, you've got these little localized features inside the wave, which pretty much involve a very large scale separation between the wave itself and the small scale bursts they create within it. So you need some kind of element type approach. It's what we call a multi-domain approach, kind of showing it in a cartoon. Internally, within these elements, I have a certain grid that I'll talk about in a second, right? Which is associated with higher order polynomials. I built a code back in the day where I could study flow processes in a box that is pretty much just a nice rectangular box and cannot account for any variable bathymetry. And my box on a horizontal plane is periodic, so I use a Fourier discretization. In the vertical, I have this multi-domain approach that I talk about. This really limits us in the type of solutions we can get, or the type of phenomena we can simulate. So we wanted to go beyond it, and I had a first student that I put to taking the doubly periodic box and making it doubly non-periodic on a depth, on a stream, let's call a stream depth plane just in 2D. And he got pretty far, but he didn't get to the full thing, All right, and I'll talk to you a little more about the numerical methods as we move forward. So I told Sumedh, you're going to deform this box, my friend. This was not an easy task. Okay? So to give you a little more context, this is an internal solitary wave captured through acoustic measurements, basically reflection of the acoustics of critters or particulates that's hanging out in a water column. This thing's about 300 meters long and about 150 meter deep water, and it pushes down this little layer here, which is the pycnoplane that I talked about, I think by about 35 meters here. All right? So at the same time, we have these localized little patches that are linked to what's called a Kelvin-Helmholtz instability. Some of you may have heard of it, but these are little vortices. That the vortices themselves are much smaller with respect to the wavelength of the wave and the amplitude of the wave itself. Okay? So there's a scale separation. And then if you look at one of these turbulent events, you have a very, very big large scale, the larger whirl, and there's some very, very fine granular structure internal to it. All right? So there's a scale separation within these waves as well. All right? So they're a real challenge to capture. And in practice, some cases, when you want to simulate these waves, you'll say, okay, the heck with it. I'm going to sacrifice the very tiniest scales in here, where the fluid friction viscosity is damping things out. I'm going to run in under resolve mode. So to meet all these requirements, you're going to go towards a method that preferably uses an element-based approach, where you can focus the elements where most of the action is happening, like, let's say, somewhere around here. All right? We're not going to talk about bathymetry refinement, anything like that. You want the method to be clean of numerical diffusion, so you won't diffuse off of the grid scale. You don't want numerical dispersion that's going to produce artificial waves that shouldn't be there, or produce waves moving with the wrong propagation speeds. And at the same time, you have to keep something that's robust at what's called in an under-resolved context. All right? So when you have a nonlinear phenomenon, there's a nonlinearity, and you're thinking in a multi-scale context, the existing scales will typically try to produce scales that are progressively smaller, and eventually you're going to hit your grid resolution. All right? So if there's no natural dissipation in your system, often these methods break down. All right? And there's this issue of non-hydrostaticity. That also produces a bunch of other problems in terms of solving what's known as a Poisson equation. All right? So there was this ambitious endeavor to use these very accurate element-based techniques, and I'll get into like the essentials of those, to model waves of this kind and eventually to break down. So one student spent about 5 years on his thesis, and Sumedh comes in. All right? And he has an applied math background. He's a little bit familiar with high-performance computing, so he's the most promising candidate possible. So, what are the equations that we had to deal with? Okay, these are the incompressible, fully non-hydrostatic, fully nonlinear Navier-Stokes equations. This is the Ph.D. that is my bread and butter. It's why I make a living. Okay? So I'm looking at it in a two-dimensional context. So I'm just considering two components of my velocity field. All right? My two unknowns. And I also have density perturbation that I have to work for. There's a thing called the Poissonist approximation, which is saying the following. It's assuming that initially if my water is not stratified, there's not a temperature salinity stratification, I have a uniform density across the water column about, 1,020 kilograms per meters cubed. There's a little gradient which is pretty much produces a small difference. Let's say we're across 10 meters, is about no more than 5% of the typical value right here. And to that gradient, there's also a very, very small disturbance that's produced by my internal waves or my turbulence. So a key difference is with other people in fluid mechanics that work in what are called compressible or reacting flows, where they get differences in density of the order of 700%, we're looking at differences in 5%. But the stratification suppresses turbulence typically, and it also can support internal waves, right? This is the physics. Now here's the equations. I know some folks, if anyone's challenged with color blindness, I apologize. It's just, I like to use a lot of color here. And I thought I'd use green and blue for the most benign operators in these equations, and the red and purple are the two more evil ones, okay? So first up, you've got the equation for the horizontal velocity. This is the vertical velocity. Here's the equation for the density perturbation. It's an advection diffusion equation, or advection dispersion, depending on what discipline you work in. And here's this little punk right here, all right? It's just a constraint. And I'm not an optimization person, but when you hear the word constraint, you might think of various things. But this is telling me that my fluid needs to be incompressible, right? So if I've got a block of fluid, and I compress it like this, it's going to respond in this direction to compensate and maintain the original volume, basically. All right? So when I look at each of these equations, I'm going to start with the blue and the green. These are my Laplacian viscosity terms, all right? What these tell you is that if there's a disturbance at a certain scale, or like a little localized disturbance, viscosity would just smooth it out and spread it out and attenuate it, all right? equivalent term down here in the density equation. Here's a term that causes a feedback or connection between the vertical velocity equation and the density equation. If I create a disturbance, so think of a stratified fluid as being a collection of layers. If I disturb this layer, it's going to feel buoyancy force. It's going to want to bring it back to where it is. All right? This is the buoyancy term. Okay? These do not pose dramatic challenges in numerical modeling, right? To first order. The two evil terms are this guy and the purple one, right? The red term is a nonlinear advection term. It's the fluid moving around its own momentum. But in a mathematical context, where it becomes interesting is that a certain scale starts to create progressively smaller and smaller scales. It will force you at some point to create patterns that will hit the resolution cutoff of a grid, right? My PDEs live on a grid all the time. You'll see an example in more detail in a second. Then there's this other term right here, which is linear, and you're thinking, it's not that dangerous. Nevertheless, it's one of the mechanisms through which the various momentum equations are coupled, and its role in a mathematical context is to enforce this incompressibility right here. Now, a lot of folks in environmental flow modeling, or geophysical flow modeling, will use what's called the hydrostatic assumption. They will say that pretty much the accelerations in a vertical are very weak and very negligible, so I can throw away this term right here, all right? And pretty much, you have to pretty much just worry, so you throw away these two terms right here, and neglecting viscosity for a second, you pretty much integrate in a vertical, downward, using the density to get a nice immediate prediction of what your pressure field is. You plug it in the horizontal one, and you keep on moving. Right? This won't work well for turbulence or internal waves because I have very strong vertical accelerations. I cannot neglect these two terms right here. And as a virtue of that, I have to solve a Poisson equation. All right? So typically when I solve these PDEs right here, I start at some initial time with an initial condition, and I move and I march forward. When I go from my level n, let's say, to level n plus 1, I treat each one of these operators independently. Right? And you'll see this thing repeat itself over and over. I will first account for explicitly the role of these nonlinear terms. We'll get an updated velocity. Then I end up working with a pressure equation because of the non-hydrostaticity, which is completely evil. It's going to be 1/2 of this talk. Right? I solve for the pressure. I update the velocity to account for the pressure, and then I hope to get an incompressible field, or a solenoidal field if you want to use terminology closer to yours, that honors this constraint right here. And then I apply typically my boundary conditions through these viscous terms right here, usually invoking various implicit solvers. All right? So what Sumedh really focused on was he built this amazing flow solver that could simulate the wave phenomenon we talked about. But mathematically, his key challenges were to solve the Poisson equation that comes out of this. We'll talk about it in a second. And also to make sure that this constraint is operative, because there were some new challenges due to the particular method that we used. So, first little snippet. All right. So he started working on this stuff, and he told me, I'm gonna rebuild stuff from scratch. I'm gonna use all these libraries. I got it going on. I'm good. And I went on sabbatical in his second year. I came back. We're starting his third year. He still got a lot of momentum and enthusiasm. We sat one Friday around this time in a small room in our building, and he told me, Pete, I'm ready to quit. And I take a lot of inspiration as to how I try to operate the group and how I try to guide or mentor folks. It's from my own experience as a basketball player, and I refer to some of my coaches, especially one about whom Sumedh knew a whole bunch, and who told me that Sumedh is going to be your Michael Jordan of graduate students, even though Sumedh hated that characterization. That meaning that this kid is very capable, but you've got to give him room to breathe and do his own thing. So I said, fine. If you want to quit, quit, but we've got something really beautiful we're getting very close to. So we had a long chat, and I think the experience humbled him. I try not to be a taskmaster. I don't think I am. Talk to the folks in my group. But I wanted to guide him in such a way where he could acknowledge the difficulty of this project. And once he got to that point, ironically, the next day I think there was a New York Applied Math conference that David was hosting, I think. And he showed a poster, and Zach Clausen came up and gave him some idea about the Sherman, Morrison, Woodbury identity. And he said, this is it. I know how to work out the problem. All right, so then everything started going in an upward trajectory. So the moral is, everyone's going to hit a wall during a thesis, but you can get past it. All right, and I saw this guy who was fearless, super independent, really creative, He told me, I'm going to create my baby here, right? This is gonna be my child, this flow solver that I will build. And it's really true. It's amazing what he did. And he worked close with a friend of his who was a software engineer at Applied Research Labs in Texas, Greg Thompson, who really taught him the principles of proper coding practices of high-performance computing. He helped make the code about 10 to 15 times faster, I think. And I got to know Sumedh as someone who had a very healthy level of obsession, a lot of initiative, very innovative, and he would never hesitate to challenge me and tell me that your ideas are wrong or going in a wrong direction. But he did it in a really respectful way. He challenged everyone in the group, but at the same time, he would always really listen. I would also tell him, you're very scattered right now. You need to prioritize. You need to focus. So we had this pretty dynamic rapport that I think, among other people, would might even cause some injury. We managed to do that and go forward. So what did he create? All right, so this is an actual real transit from the South China Sea, all right? Where's a place which is the paradise of internal solitary waves that I talked about. Here's a simulation that he ran where you're looking at density isocontours, and you're seeing successive snapshots of such a wave. It starts at 700 meter deep water, and it's going out from like over a transect about 63 kilometers long. This is the initial internal solitary wave, right? To compute this is a very complex nonlinear eigenvalue problem you have to solve. It's an exact solution to the viscid version, so the equation I just showed you earlier without the viscous term known as the incompressible Euler equations. So you put this in as an initial condition, and it just moves and marches up the slope, and it starts steepening, and depending on some other other effects, it can actually produce a lot of complex internal phenomena internally. Right, and here, these little lines here delineate what I call a subdomain or an element. Within each subdomain, my solution is a 2D approximation using Lagrange polynomials on a Gauss-Lobato-Legendre grid that I'm showing you right here. All right, so I'll show you a little movie just to get an idea of what he did. Unfortunately, it's not playing in a projector, so I'm going to have to bring up this guy right here. All right, where is it? So you're seeing the wave starting out. The deeper part's not really, you don't see the departure in really deep water. As soon as you start feeling the bottom, it steepens up. It doesn't break necessarily for this test case, and then readjust. And there's work that Gustavo's doing that's actually capturing these waves, produces really interesting little breaking effects with some very, very localized granular structure right in here that you can't see, unfortunately, in this movie. So what he did, through the numerical mathematics, he managed to construct a state-of-the-art flow solver that allowed us to attack a very rich range of fluid flow problems. All right? So I will try to talk to you. I'm noticing I'm like going way slower than I expected about the two problems that he worked on. Okay? And we'll see how far we can get. And I remember last time I gave a talk here, I machine gun through it. I do not want to do it this time around. Okay? So the idea is, as I said, we have this PD that we're advancing across successive time levels, and within each one of these set of PDEs, there's these three key operators. So in a sense, I treat each operator independently, and when I deal with the pressure and the viscous terms, I have typically some PDE that looks like this, a linear operator acting on my unknown variable, forced by right-hand side with certain boundary conditions. And I'm doing this, I'm working with this equation on a grid. And this is an idealized grid just on a box domain. And you're seeing pretty much 6 subdomains in this direction and 2 in a vertical. Notice the grid here. This is pretty much linked to using a Lagrange polynomial-based nodal approximation to my function. I'm working with higher polynomials. These are very similar. These are a variant of your Gauss quadrature points right in here. Okay? And you're seeing in green the subdomain points, right? The interface, subdomain interface points. So the idea is that in the interior, you have your PDE, okay? But at the boundaries, at the interfaces, you're using a combination of the PDE plus either the boundary condition or the actual interfacial patching condition as it's known. All right, so depending on the operator, I have a particular communication condition at the interfaces. I won't get into full detail of that yet. It's some localized Robin condition, usually, or it could be a localized Dirichlet condition that pretty much requires that certain fluxes of the variable of interest are balanced across the domain. All right? So what I do is I pretty much penalize the operator at the boundaries of the interfaces with the corresponding boundary or internal condition. In a sense, what this does is that my solution across these interfaces has a very, very weak discontinuity, right? It does not have a great physical implication, except for one little feature I'll talk about in a second, right? But it provides a lot more robustness when I'm working in an under-resolved mode. So if I've got a nonlinear operator trying to produce smaller and smaller scales below my grid resolution, the use of this approach pretty much relaxes the desire of the nonlinear term to produce stuff below the grid can't see that stuff, and that produces numerical noise and blow up your solution, right? So this provides numerical stability. That's why we like it. I can get into it later if you want to have a discussion. All right. So we use what's called the collocation approach. For those of you that have worked with weighted residual methods, Galerkin methods, this is an approach where your test function is actually the nodal or modal basis function, nodal in this case. It makes the implementation a lot easier. And the key thing is this continuity that I talked about. The solution can jump a little bit. And this makes, when you're running an under-resolved mode where you can't see the fine-grained features of your problem, it makes the numerical solver significantly more stable, all right? And therefore, we can often work with cases of more intense under-resolution, all right? Well, let's focus on this equation right here, and let's discuss the particular one that we deal with in the context of the pressure, all right? So I'm going to switch symbols here. This is an argument I always had with Sumedh. Any fluid mechanicist uses U for a velocity. He's an applied mathematician. He uses this for pressure. We typically use P for pressure, but I want to honor what he showed originally. So you solve this Poisson equation right here with a boundary conditions of the Neumann type, right? This spells evil immediately. We'll talk about it a little more. These are the interior interface conditions, right? And they're of the Robin kind, right? So this is a gradient operator of my pressure projected on the normal vector of the interface of these subdomains that I just talked about, right? So what you do is you discretize this. You discretize your domain with a bunch of subdomains, mx and mz in the x and z direction. And in place of this continuous equation, you have to solve a linear system. All right, and I will use the term R right here, the symbol R to denote my total number of grid points. P means the number of grid points in each direction in each one of these little fellows right here, right? So P is typically between 8 and 15 in our application. So it means that I'm trying to present my solution with an 8th to 15th order two-dimensional polynomial inside the grid right here. Okay? So this is not easy to solve. It suffers from a lot of things that we'll talk about in a second. And the operator becomes, when I start looking at the matrix, when I start looking at the operator itself, there's a bunch of Jacobian terms to pop in. It's a lot more complicated than what I'm showing over here. So this is sort of the box element approach, a box domain approach. When I deform my boundary, this becomes a lot more complicated, as does the corresponding matrix. Okay? But it doesn't impact the generality of our discussion. So, and U is pressure, and it's what's called the pseudo pressure. For those that are fluid mechanically oriented, it's the integral of the pressure field across one computational time step that has to do with the time discretization of your PDE. Okay? So why is this difficult? Number one, it's an elliptic problem, all right? So everything is coupled across your grid, infinite speed of propagation of the information. So if this is my computational domain, I ping right here, it's going to feel what's going on down here immediately. My matrix is going to be huge, all right? So as I said, P between 8 to 16. Practical applications, I might have about 1,000 subdomains in the x direction. I'd say about 10 to 20 in a vertical. You go do the numbers. We're looking at matrices that have dimensions about 1 billion by 1 billion. Okay, so I have to think iterative methods. The collocation method that I talked about gives rise to certain discrete differentiation operators, or discrete methods of derivative calculation that are matrices that are non-symmetric. All right, that creates its own set of challenges. You can appeal to certain iterative techniques that are a lot more comfortable for people to use and a lot more efficient, like the conjugate gradient method. All right. The problem is singular due to the Neumann boundary conditions because the solution is not specified beyond up to a certain additive constant. You can work around that fairly easily, but there's also a compatibility condition that links the right-hand side into boundary conditions that gives rise at the numerical linear algebra level to a solvability issue of the linear equation, the linear system of equations that I showed you. And that's even more difficult, but there's ways to work around it by projecting out of the space of a right null singular vector of the differential operator, the discrete differential operator. And because of the higher polynomials, this is ill-conditioned, right? So we're going to have to solve this iteratively, but the properties of the discrete operator are not very favorable, right? And anyone that does incompressible flows, the Poisson equation solver is the big challenge. And we were faced with this even worse, right? It made our life even more difficult. Okay, so the first student spent 5 years, he got something that was semi-functional but could not be applied to environmental problems. And Sumedh said, I'm going to use, I'm inspired by the Schur-Morrison-Woodbury type of decomposition of a theorem for a matrix. he read a bunch of domain decomposition literature, and he said, I'm going to go that route, and I'm going to use the Schur-complement method. All right? I barely knew what a Schur-complement was when we started out. I'd seen it in the literature. I didn't know much. So this is my disclaimer that I'm not an applied mathematician. Okay, so here's one of these grids, right? And this is the discrete, the operator that results, the matrix that results from the discretization of the Laplacian operator in my Poisson equation that I showed you. All right? In the context of the particular grid, I can break this down into two parts. All right? There's this submatrix A that's operating on the values of the grid that are internal to these subdomains. And there's this part right here, which is operating on the actual interfacial values right here. So the grid points, the solution that lies on the grid points on the interfaces, this is the guy that acts on it. All right? And pretty much, your B is a discrete version of that local Robin boundary condition, in a sense, okay? And E is what's called an extension operator. They'll take everything and put it back in the right place in a full matrix, right here, okay? So what Sumedh said is, I'm going to isolate the problem. I'm going to focus on dealing with the red points first, because the internal points are a lot easier to solve, and then I'm going to connect the two solutions together. I think people have done this before, but he was the first to do it in a context of these discontinuous type of discretizations. And there were certain very numerically favorable characteristics that emerged in this way, and that was where the originality of his work lied. Okay, so here, previously here, I'm thinking about breaking my domain, both cutting across the interfaces in a horizontal and a vertical as well. Right? In this case, I'm just going to cut across in a vertical. Because remember, the problems that we typically are going to look at are these wave problems that consist of waves propagating over very, very, very long distances. Therefore, I have very, very, very long domains, right? So typically my domain, my subdomains, the number of subdomains in the long wave propagation direction versus that in a vertical is much bigger. So it's a lot more efficient to cut like this, all right? So in this little cartoon example, it's a 4x4 subdomain domain. I'm just cutting in a vertical, okay? And I am taking the multi-domain penalty discretization of the Poisson operator, and it produces this matrix L, all right? Just for the sake of illustration, the red entries, the red elements, are those that correspond to the coupling, the communication conditions of subdomain interfaces. The blue are the points that correspond to the points in the interior of these slices right here. And I can deal with these a lot more easily and a lot more directly. This is the challenge right here. All right. We actually went over and talked to David about this back in the day, and he gave us some really illuminating guidance. We're able to do this in 2 dimensions. I think in 3D, when your subdomains are bricks, like 3-dimensional elements, there's an issue of dealing with these folks in a pretty much direct fashion, as I'll talk about in a second. But the problems we want to work on are very, very long domains, all right? They're 2-dimensional, really long 2D slices. And the worst case, I can assume that my domain is not going to vary in the x direction. But so my wave is going to go up in a 2-dimensional kind of fashion, but any turbulence embedded in a wave can be done in 3D using a Fourier discretization. If that makes no sense, don't worry about it yet. All right? So this matrix here has these 2 key parts. A, contribution of the interior points, all right? And E times B, which is the role of the interfacial points. With the help of my extension operator E, they're put in the right spot in the matrix. Okay? So this is to give you a little more of a better visual idea. These 2 matrices are not square, but they conspire together to land the corresponding entries into the original matrix. We're going to focus on these fellows. We're going to solve their contribution iteratively. So I'm going to try to give a little more detail. And I'm realizing that I probably am not going to cover the other topic that was part of his thesis, because we'll probably run out of time. It's best to have a discussion. Okay, so here's the grid, 2D grid again, just for the sake of illustration. The original full system is complicated to solve, and it's tough to store the matrix, all right? And it's a beast to do iteratively, so that's why we're following this whole strategy right here. And Sumedh's idea was like, let's just look at a vector, all right, that involves only the interfacial points, right? And pretty much that is the vector of the discrete Robin patching condition operator existing locally at the subdomain interfaces, acting the solution only on the interface. All right, so he's going to build a linear system that just deals with the unknown values at the interfaces on which we're operating with the discrete patching type of operator. Okay, so a bit of the linear algebra. You can write this out in this following form right here. right, you can exploit the fact that you're defining a new variable, which is just the Robin conditions at the interfaces pretty much evaluate those grid points in an approximate sense. Here's your original linear system, so that you have, this is the definition of this new variable b, that's the second rule. Here's the original linear system, all right? And you can write it out in this form, all right? So basically, anything that satisfies the above equation right here also satisfies the original linear system L times U equals B, all right? And then you can write this out by using, you can actually appeal some Gaussian elimination, which is really simple. It's a 2x2 system. So you're left pretty much with these two fellows right here, all right? So you're just doing backward substitution. These are blocks, of course. They're not individual entries. You have, at the bottom right corner, an equation for your new variable v right here, which is the role of the interfacial points. You solve for that first, and then you have another linear system where now you've taken care of v, where you have to deal with the role of the internal points. And this involves the inversion of this matrix A, all right? As we said, A is the contribution of the internal points. If I'm using a parallel code, A is not that big a matrix. I will try to do this by using an actual direct solver, so an LU factorization, right? If I'm doing it in 2D. So this is fairly easy and straightforward to do. This is the tougher point down here. It's a smaller system, but it's big enough, all right? And this is called the Schur-complement system that we're focusing on. All right, so I'm just changing notation a little bit. This is what the end of this, the linear algebra, the upper triangular system that resulted. We're going to focus on this fellow down here, all right? Inverting the A's is not very hard. I define a new variable called, on my right-hand side, called B sub S, where this is the Schur-complement matrix S right here, all right? It's this guy. And pretty much what I gotta do is I gotta solve this equation right here, so I have to effectively invert this fellow, okay? I get those interfacial points as I said, and then I also solve, and I back substitute and I solve for the role of the internal points. I assemble everything together and I have my pressure field on a grid, okay? Not that straightforward, but definitely I think it was a very innovative idea. Okay, so I'm gonna focus on this little system right here. That's the Schur-complement problem, all right? Again, here's the definition of the matrix. The internal operator, the internal grid point operator, easy to invert. This is the communication operator on specific, it's a non-square matrix. Here's the extension operator. The key thing is that this system is definitely smaller than the original full system by a factor that corresponds to the number of grid points in each direction. This is what P stands for, but it's still pretty large. The good thing is, and this is where Sumedh did some really nice theory, he proved it, the conditioning of the smaller system is incredibly better, right? It's definitely smaller by a significant factor, right? It's a sparse system because our original matrices were sparse to begin with, all right? The issue is though, of course, that it's non-symmetric, all right? So it's inherited by the fact that I'm using what's called a collocation discretization for the PDE, and I have a bunch of non-symmetric operators, right? And it is also inconsistent, okay? There's a compatibility condition that's linked to a certain ill-posed nature of the problem. We have to adapt the right-hand side accordingly to get a solution that we desire, all right? So this Schur-complement is still, the Schur-complement problem is still pretty big. We have to do it iteratively, and we have to do it efficiently, okay? So Sumedh had to worry a lot about algorithmic scalability, and we're still worrying about the parallel scalability of this algorithm. It's good for starters, but it needs improvements. So what he said he's going to do, he's going to solve the linear system with a Krylov subspace technique, the generalized mean residual method known as GMRES, that's used for non-symmetric matrices. And he's going to precondition it, right? There are people in here that know incredibly better the world of numerical linear algebra than I do, but I know when I see the term preconditioner, sometimes I think of the term black magic, all right? So I will give you my very humble perception of it, and I'll try to explain first why it's needed. So again, this is a toy problem. It's a domain that's got an aspect ratio of about 50 to 1, often common for these oceanographic problems, long domains, waves shooting over long distances. Just a square box with a manufactured solution. We're solving a pressure equation here only, all right? It's not a fluid simulation. And it's just one run to solve this little toy Poisson problem. And you see that pretty much if you look at the L2 error, I believe this is the L2 norm of the error of the actual solution is comparing successive iterates. You see a somewhat slow convergence of the solution over about 400 iterations, all right? There's no preconditioner involved here. We're taking the discrete problem and we're just hitting it with the GM-res method, right? And then suddenly everything drops, boom, really rapidly, right? But you do this every computational time step in a fluid flow simulation, right? And a fluid flow simulation of any practical interest will involve about 100,000 time steps to, if you're lucky, 10,000 time steps. So the waiting time thing is incredibly long, all right? And the issue is that you have a very, very large matrix. And in a matrix context, all elements of the matrix are not immediately aware of one another. So the top, let's say the top left corner doesn't really know about the bottom right corner. In a sense, in the physical equivalent, in my interpretation, is that if I have these very, very long domains, it's an elliptic problem. What goes on at one end doesn't really know what goes on the other end, but by virtue of the operator, they still remain coupled. Okay? So what Sumedh said is, what's going on here is, if you look at this operator, it's got certain eigenfunctions, discrete eigenfunctions that describe it. And there are those that have very slow variation over the whole domain. This is what are called the slow eigenmodes. The discrete equivalent that appears in a matrix that I discretize is what's causing the very slow convergence. So I should try to deal with this. And he said I got to figure out what a preconditioner is. So this is one way to think of preconditioning a problem. I know there's different formulations. Here's your Schur-complement problem. The idea is, can I come up with a new variable that's the inverse of this preconditioner matrix, multiplying a new variable will give me the original one. So I have to solve this problem right here, but the hope is that M is in some sense, I'm not writing included there, I'm sorry, it's similar to the original matrix S. It's easy to compute. In the end, it has better spectral properties. All right, and when you're not a mathematician, these statements can be awfully frustrating, right? Because to build M is not trivial. And we spent years talking to Charlie Van Loon early on. We bothered David. It took a long time to get to something functional. All right, so you can use the simplest approach. You can say your M is going to be diagonal. It can be block diagonal. It can be some partial factorization of the original matrix. There's all sorts of tricks you can do. But I think Sumedh took it further. All right, so what you do is you build this at two levels. You have a preconditioner that takes care locally, sort of within subblocks of your matrix. And then you need a preconditioner that connects across the whole matrix. That's called the coarse level preconditioner. Right? I could spend hours talking about this. I'm not the most specialized person. So I will just try to give you the basic idea of what he did here. Okay? So he divided up the problem in two parts. He said, the first thing I want to do is I want to isolate the contribution of the slow eigenmodes, those that couple across the whole domain, and just deal with those directly. So in a really rough sense, I have to project out to a coarser grid and solve a corresponding linear problem directly. And then I'm going to focus on a higher eigenmodes to the ones that converge rapidly without a problem, as long as I find the right precondition. So those of you that are, in your eigenvalue focused courses, you may have heard of deflation methods, right? This is how the problem was isolated. In practice, I even struggle to describe exactly how he did it, all right? And then he focused on a contribution of, in terms of the projection of the solution on the eigenmodes of my pressure operator, they're the ones that were faster varying. So you typically take 4 or 5 of these slower eigenmodes, you deal with them directly. There's a bunch of others that you worry about to solve for iteratively. And you solve the iterative problem, and then you couple pretty much everything back together. All right. These are some of the key points of the deflation. I will admit, I do not know how to explain these indicator matrices. And actually, during his exam, there was some really useful feedback that was given by the committee. I will leave that. All right. So this is the basic idea of how a block diagonal preconditioner works. The preconditioner operates in 2 levels. What he did is the following. So once you get rid of these, through the deflation, you get rid of the very slow modes of the solution, and you focus only on all the faster ones. When you build the Schur-complement matrix, it looks like something like this. All right, so if this is a grid, these are the interfaces between 2 successive cells. It should be red and not green. So this stuff corresponds to this guy down here. I would ideally like to make it green. What you do is you view all of these guys as individual blocks, and you apply what's called the block Jacobi preconditioner that involves just the inversion of this block right here. So for example, this fellow. This is one block, the next block, the other block, onward and onward. Right? So as far as I understand, for the fast modes of the solution, this is sufficient. It also takes care of what's known is the high aspect ratio issue. All right, so these subdomains, often in environmental flow applications, because the full domain is very long, the subdomains are also very long and very shallow. Right? And Alex is in the back. I think this is a big challenge with type of methods everyone that works with higher techniques is faced with. I don't have the exact explanation, but this type of approach to preconditioning helps things operate a lot faster. And usually the longer your subdomains, the worse the conditioning of your matrix, the convergence of the iterative method goes down the drain. This approach managed to totally remedy that. All right. So ultimately, what Sumedh came up with was this deflation approach, mixed with the Bloch-Jacobi preconditioning of the faster modes combined together. It improved the convergence of this method dramatically. So here's my toy example. All right. The number of iterations to get down to desired tolerance went from about 580 to 10. Okay. And this applied for all the various geophysical problems we were working on. So we've got a super rapid solver that allowed us to explore the problems we're talking about, right? So this traditional method falls apart. This is the technique he developed. There's also these additive Schwarz type of preconditioners. He found that his was 20% faster, but that's not as much the key point of the discussion. All right, so we were able to look at problems like this. There's an oceanographer colleague at the University of Washington that has done measurements of such waves off the South China Sea. What we're working on right now is to model this in 3 dimensions where the transverse is assumed to be periodic. So the wave itself is not going to vary in the transverse, but the turbulence within it can actually have a certain fine granularity that also varies in the transverse direction. Right? So here's like for a sample wave propagation problem, what this approach of dividing it up in subdomains. I mean, there's a lot more subdomains here there are in this cartoon down here, but pretty much this is how you isolate the various blocks of the Schur-complement matrix and you proceed to solve it. Right? So this is a fairly superficial description of this problem. Okay? But the key point is he built this pressure solver that was uniquely designed for element-based techniques at high orders that were discontinuous across the element. All right, so he exploited a lot of these features and produced something super rapid that earned a publication in the Journal of Computational Physics. All right, and it was all his work. Greg helped him make it faster. I helped make the text a little more approachable. So I probably want to take about another 15 minutes, if that's fine with the organizers. I'll talk a little bit about the second problem, but I don't know if I'll do it in full, because I think that there's some other things that are more important. One thing was that Sumedh I'll start by the fact he was an amazing communicator. Straight shooter, very clear, made the point. It was a pure joy to talk to him every single time in my office. He was a great teacher. He didn't realize he wanted to teach, but he TA'd my undergrad numerical analysis class with John's in the back. They both made a fantastic team. It was a 1-2 punch, along with Abby, an undergrad TA who worked part-time. The students loved him, and I think a lot of us remember him in our room, or probably the CAM folks remember him maybe in front of a whiteboard over here, just delineating out the most beautiful proofs, or just the most beautiful outlining of equations, right? The guy was an artist. He could really connect to you in your mental and emotional state. He was an amazing listener. He would really engage you. The discussions were really in depth. And I think whenever he walked into the room, the guy just radiated enthusiasm. It was amazing, right? He never cut corners. It was really direct and very ethical. I think he was a great team player. Whenever I needed help on proposals or anything I was drowning, he'd tell me, Pete, I got your back. I got you covered, right? That was beautiful. And the guy had this really dry, sarcastic sense of humor for anyone that knew him. So that added to the whole picture and made it a real joy to work with him. So I would like to tell you maybe about 10-15 minutes about his next project, but it's probably the order of 20, so I might skip through stuff, but I want to give you an idea, all right? He worked on 2 problems on higher order methods that both allowed us to build the state-of-the-art flow solver tool. And the actual description of the flow solver was the 3rd chapter of his thesis. What I showed you was the first. We'll talk about the intermediate stuff right now. Okay, so here's his little subdomains again. So the key thing is our flow solvers need to be incompressible, right? I got what I call a volume of fluid. I compress it. It has to respond to maintain volume. Okay, and the way to check on it is to take the divergence of my velocity vector. It should be 0 every year. For all practical applications, it has to be much smaller than a certain value, hopefully at least 10 to the minus 6 throughout my domain. And we're working with these higher order methods, and we're pounding the gospel of trying to make this more and more meaningful. But in a lot of practical problems, especially when we're saying what we call under-resolved mode, right? So we're missing the very, very fine-grained features of the solution. If you compute the gradient of the u vector you would find it was really bad along these interfaces, right? So that's on physical. In some cases, it would produce certain jumps in the solution that the nonlinear term I talked about would pick up on and expand upon, try to build smaller scales that would kill the simulation. And I'd seen that for years. I did not know why it's happening. There was a group at the University of Waterloo. Our friend Chris did his Ph.D. there. They came up with some ideas where they said, okay, let me design some new modified basis functions in here and take the solution and project it on these new basis functions, which have the key property that by definition, divergence of these basis functions is 0. All right? That's pretty complicated to do, to build the math. And you get these weird vector basis functions, not nice Lagrange polynomials anymore. And they also found that it didn't work in the end because you still started getting, your divergence was beautiful, but still things still blew up on these interfaces. And I told Sumedh, here's a guy to try to tackle this for me, please. Okay? And he was a little hesitant. And I was working in France for the summer of 2015, and we started firing these emails back and forth, having Skype sessions with him and the former student at Waterloo, Derek Steinmoller. And something happened, and this idea exploded. And the two of them really took off and came up with something very beautifully creative. And what I want to say about Sumedh as an applied mathematician was, we have these PDEs, right? Each operator represents physics. It's the advection of the fluid, it's diffusion, it's pressure communicating information across the grid. In the end, you get these weird matrices. And I remember going to Charlie Van Loan, he's not here, and Charlie would tell us, just show us the matrix, just show me the matrix, I do not care where it comes from, and then I'll do my magic with it. And I wanted to couple the matrices with the physical operators at the same time by taking into account the discretization. And Sumedh somehow really tuned into that, and he had this magical ability to look at these matrices and understand the physical processes that generate them, and he would look at them from the point of view of the singular value decomposition. He was the ultimate HCD maniac or addict, if I might say that, but he used it in a very creative way. So I'll try to give you the rough idea as to what he did over here, okay? So here's my Navier-Stokes equations. Incompressible Navier-Stokes, here's the incompressibility constraint. I'm not showing you this density term that corresponds to buoyancy effects. Here are the nonlinear advections. Just take a look at this right here, right? So try to build a case for this in about 10 minutes, and then we'll close. So what you do is you want to advance this temporally, okay? So you've seen in your basic numerical analysis courses how to advance initial value problems, all right? The idea here is we're going to apply, just for the sake of illustration, a forward Euler time-stepping method, right? We use a lot more accurate methods, but the forward Euler will show you the idea a lot better. So what you do is you say, on the level n, I've got some velocity vector un, all right? And I will pretty much, in a forward Euler context, I'm going to break down this fellow into two parts, all right? I'll first take care of the role explicitly of the nonlinear terms, and I'll update my velocity having computed the nonlinear terms, and I will get something called u hat. And then I will go to the next step where I have to get my final velocity, but I've got the pressure hanging out here, all right? The infamous pressure, which we have to build that very sophisticated solver algorithm, all right? So what I do is I write things in a slightly different form, all right? I say that my new velocity will become the original velocity, the one that was created, the previous step, updated by the gradient of the pressure, all right? And this involves what's called the Helmholtz decomposition theorem. In a sense, you're saying that this fellow here, the most recent update involves this guy here. It's the gradient of a scalar. If you take its curl, it goes to 0, so it's irrotational, has no vorticity in our terms. And this is going to be, ideally, the solenoidal part, all right? So the hope is that this step, once p is computed, will produce a velocity that is solenoidal, right? That it has a gradient that goes to 0, is identified over here, okay? So this is the key, the two key sets of equations, and I'm putting them back up over here right now, all right? This is the second step in the time stepping of the two operators, and I split them in half. And here's what I want to get, right? And what I do typically, I'm hanging out at this level, I will take the gradient of it, pretty much, so that will produce, I take the divergence of it. This will produce a Laplacian, so this is the Nobel operator squared, right, of the pressure equal to this right-hand side right here. I want this fellow to be incompressible, so I assume that it goes away. So pretty much I have to solve this equation right here. And just in a sort of symbolic sense, I can say that pretty much this pressure that I get is the inverted Laplacian multiplying the gradient, the divergence of the velocity at the previous step. All right. So then I can say the following. I'll get rid of this fellow right here. I will pretty much say that if I recombine all the algebra right here, that my final velocity, the new time level, m+1, is equal to an operator called p here, acting on the velocity that contains the information. It's an intermediate velocity, has no physical context, contains the information from the previous time step. All right? And if I use pretty much, it's initially the previous velocity minus the gradient of the pressure, all right? I've said that the pressure is equal to this beast right here. Here's the gradient operator. Here's my estimate of the pressure. Pretty much I can say that the new velocity is given by the action of this fellow right here that I will explain immediately. It's called the projection operator. It basically projects my solution to a space of functions that are pretty much solenoidal, right, to respect this incompressibility constraint of the physics. So here it is again up here, all right? So this is what I have. And the idea is now that, of course, I'm operating discretely. I discretize everything. I discretize my operators and my function on a domain on a grid, okay? So to do this discretization, I'm going to have to be able to discretize all these little critters right here. So I need to define, first of all, a discrete divergence operator, which is going to be acting locally at each domain, and then I'm going to concatenate them all together to build pretty much a divergence operator that acts on a whole domain. It's going to be basically uncoupled blocks that correspond. It's this weird matrix. It's going to have a bunch of uncoupled blocks that each one is going to work on an individual subdomain of the subdomains that I just talked about earlier. Right, so these are just differentiation operators. And you've got the contribution of the vertical and a horizontal direction, right, that act on a horizontal and vertical velocity to compute a divergence. So if you apply this matrix here onto your velocity field on a grid, it should give you a discrete estimate of the divergence. Here's a corresponding gradient operator. If R is the total points in the subdomain, I'm giving you the dimensions of these matrices. They are not square. That's the key point. These two are not, you're seeing the structure right here, but in practice, if I take the transpose of this guy, it's not going to produce G right here. Okay? It's simply because these matrices originate from what's called a collocation approach that gives rise to inherently non-symmetric matrices at the subdomain level. Okay? In the end, you have also your discrete Laplacian that you can either discretize whichever way you want. In our problem, it's discretized through this penalty approach. Just the idea, operator is discretized in the interior, and I account for the role of the communication of the subdomains for this penalty term at the interfaces. Okay? So practically speaking, if I have what's called, I don't worry about these discontinuous approaches, my discrete Laplacian is equal to my divergence matrix multiplying my gradient matrix. Okay? If I don't have this penalty approach. So my actual operator up here, P, which is operating on a previous velocity, is going to bring it into this incompressible function space, in the solenoidal function space. In discrete sense, is equal to this fellow. Here's the identity matrix multiplied by the gradient operator, the inverse of the Laplacian multiplying D. All right. So there's a lot of dark information hidden here that will really mess up an incompressible flow calculation, right? Your hope is that this guy here will come up with a very, very small divergence, right? But it doesn't. And why? And this is where, again, kudos go to Sumedh because he could connect continuous mathematical operators with matrices like nobody else could. All right? So the idea is your Laplacian operator, which normally is just the product of the divergence times the gradient operator, now for this discontinuous grid approach also involves an extra contribution, which is the coupling across the subdomain interfaces. All right? We saw that a little bit. That was the stuff that linked to the Schur-complement earlier. All right? So if I go over here and I take the definition of this projection operator I talked about, and I write it out in this form right here, this is my U hat velocity, right? I'm getting rid of the U hat because I just want to keep things clean, right? So this is the velocity that I pretty much got. Sorry, this is not U hat. This is UM+1, right? So I've treated my nonlinear terms. I've solved my Poisson equation. I got my pressure gradient. I update it. I got the final velocity. And this is basically then the action of the projection operator onto it. All right? So if I write out things in this form and I take the projected velocity and I compute its divergence, the hope is this is going to be 0. Right? I'm going to have a truly numerically computed field that is incompressible. All right? So I go out here, I do the math, And pretty much, if I can substitute in something for L, I can see if indeed, if the projected velocity field in a discrete context is truly solenoidal. And you can start asking yourself questions, and you can see pretty much if there's not this coupling term that allows for this continuity of velocity of the interfaces, that indeed this is the case. So this thing will go to 0 when C is 0. Okay? So then you start playing games. You want to look at the solution of the Poisson problem, which is this one right here. You write out P, the P vector in this function. But on a discontinuous grid, the idea is if you take the divergence of the actual Poisson equation, all right, you get this little jump operator right here. That's that coupling operator there. So if you go in here and you do some more math, and you try to identify the end result, the projected velocity, the divergence of that, if you take the divergence of that, you do a bunch of math, it turns out the divergence of the projected velocity is actually got a non-zero contribution. It has to do with the jump and the pressure, all right? And we use this jump results from the fact that I have a subdomain approach and the solution is discontinuous across it. So Sumedh found a way to remedy this, and this is where I'm thinking, I don't know how, I'm probably going to have to stop in a little bit. The essence of the idea is that he pretty much came up with two approaches. One was instead of computing actual eigenfunctions that are, actual basis functions that are divergence free, it was take the left null singular, take the singular value decomposition of the SVD of these divergence operators. The right null singular vectors are actually the discrete versions of these eigenfunctions. Use those, find the coefficients of the modal projection onto it, and then project your velocity one more step onto these new basis functions to get rid of the non-solenoidal part. Right, but he did this in a purely numerical linear algebra sense. And this is you can think of new projection operators. We're going to spend about 15 minutes, so allow me to sweep through this part. And this was pretty much the discrete idea of what our friends at Waterloo did. He then took a step further and said, the reason this is going on, this is still problematic, is that I'm projecting onto these discrete basis functions now. There are these right null singular vectors, but I'm not respecting the fact that the continuity of the solution needs to be maintained to some level. All right, so the previous approach took care of making divergence 0, but it increased these jumps at the interfaces of my subdomains and made them even worse. And he came up with this really nitty-gritty, cool least squares approach. He started going to the world of Tikhonov regularizations that I know nothing about. Okay, and this is where he taught me a ton. So there's a bunch of least squares problems that come into play. In the end, what we have to do is to get the improved velocity that it also is divergence free to some degree, all right, but also has sufficient continuity not to break down. You solve this very weird, in my eyes, least squares problem right here. So you build this in MATLAB, you build a toy flow solver that just works with some idealized problems in MATLAB, and then publish the paper. But there's multiple issues of implementation here, right? And there's an equivalent projection operator that's not truly a projection, but has properties of it. I will not get into it. And it works beautifully for the toy problems. It's very promising. And what this basically practically does, it allows us to run even more under-resolved simulations and get closer to environmental problems with an even greater degree of realism. All right, so I'm going to skip. These are like all these demonstrations to show how this new technique worked. The key theme is he produced this fantastic tool. All right, it's allowing us to explore a lot more complicated physics. It's generated a bunch of new questions in numerical linear algebra. All right, that we engineers we're still struggling to answer, so we need the help of applied mathematicians. And basically at this point, I should only put the conclusions of the talk. I cannot do that because, I don't know, I feel that there's a personal element to this talk. So I've done my best to give you a story of Sumedh's trajectory here without going into certain personal details. It was a real experience to work with him. I want to thank him, because he was really one of the ideal grad students one could find. We became friends towards the end. He produced some amazing results. He was very creative and amazingly productive. I learned a lot from him, not just as a scientist, but as a human being. He made me a better teacher. We taught together. He helped me tune into students better in a classroom. I learned about Indian culture from him in many ways, and music. And I think anybody who knew him knew that when he walked into a room, the guy would just radiate this enthusiasm and his zest for life that was really infectious. So I want to thank him. I want to thank all the CAM faculty, but in particular, Charlie Van Loon and David, who are real sources of deep insight into numerical linear algebra. Steve was his dynamical systems instructor, but also a source of general wisdom. And all three of these gentlemen were people he really looked up to. Olivier Desjardins spent a lot of time talking about the CFD side of his work. I want to talk to Alex because he was a source of guidance as far as I understand throughout his whole path, but also when we lost Sumedh, I really appreciate the humanity Alex showed on multiple levels. I had the chance to have lunch with the CAM students today. I will pretty much, I can mention these folks right here. There's a bunch more. I knew Evan more than anyone of all of his friends. The guys in our group, three of them are in the room right now, Gustavo, John, and Chris. Students that already graduated, Theodore that just arrived. He impacted them, they impacted him. I think we really tried to create a family in our group, and we try to keep that up. We're a real team. All the other EFMH colleagues, the people that we've worked on this research. Greg Thompson is the person, and he's co-authored the papers with us. He ushered us into high-performance computing. Goose Jacobs at San Diego State, worked with him a bunch on implementing particle tracking techniques. He spent like 2 months of his sabbatical. Luis came from Spain in spring to do his sabbatical with us. He's works on hydrodynamics. He and Sumedh were effectively inseparable. Frank was someone who guided him early on. These are our friends at Waterloo, Mark Stossel and Derek Steinmuller. And I want to mention Steve Lancis in this room because he was a source of a lot of perspective and guidance. So all these folks were involved in Sumedh's voyage through here, my interaction with him. So I think I've probably gone overboard with time, but this is what I had to say. So thank you, and I'll take some questions. I think we'll hang out afterwards. Thanks.
That was a really great presentation. I think it was a really fine tribute to Sumedh. And in the interest of time, though, if there are questions, I think it would be best if we save those for during the reception. And so, once again, though, I would want to.
Yeah, I apologize. What time did I start? 4:35 or something?
Yeah, it was
well for an hour. But thanks. Yeah. I guess I managed to cheat and not get corrected.